Hey everybody, welcome to some online calculus lessons. So in this lesson we will be looking at section 3.1. This is in the Larson calculus book, and we will be talking about extrema on an interval. And I think the first slide here, I'm just going to go over what we actually go through in this section. There are critical values, how to find them, why they're important, all that good stuff. We have extrema, so I'll define extrema and again how we can find those. And then we have something called the Extreme Value Theorem to round us out. Let's hop into it. One of the things I'd like to do in this section is first get out there into the world what exactly critical values are. These are going to be the driving force for this entire section. So critical values of a function are defined as x values where the derivative is either equal to 0 or undefined. That's it. Pretty straightforward. So on the next slide, we will go through a few examples on how to find critical values. So as mentioned, this is how to find a few examples on finding critical values, aka CV. So since critical values are where the function or the derivative either equals 0 or is undefined, we have to find the derivative. So as you're going through and working through 3.1 exercises, you should be finding the derivative right off the bat. So for the first example here, g of x equals x minus square root of x, I definitely want to take a few seconds and rewrite this as g of x equals x minus x to the 1/2, just so that we can use power rule here. Once that happens, we can find the derivative, and I will do that in a different color. So g prime of x is 1 minus 1 over 2 x to the 1/2. Again, that's just by power rule. So now, before we even get to do anything with this, once we find the derivative, I ask the question, is this derivative undefined anywhere? And in this case, yeah, that basically just means, hey, do we have any denominators, any variables in the denominator? And the answer here is yes. So there it is. We have to say that x is not equal to 0. So that's one of our critical values here. Because g prime of x is undefined when x equals 0. Now, we actually have to solve this thing for x. So the second part of this is we will take the derivative and set it equal to 0 and solve. So that means 1 minus 1 over 2x to the 1/2 equals 0. Now the easiest thing to do here, in my opinion, is to make sure we can get rid of the fraction. So I'm going to multiply by 2x to the 1/2. And that'll get distributed over here. And that leaves me with 2x to the 1/2 minus 1 equals 0. You can add 1 to both sides. You can divide both sides by 2. And you can square both sides to get rid of this 1/2 right here. So that means we are going to end up with x equals 1 over 4. You'd square the top and the bottom of the 1/2. So there go the two critical values for this function here. Our second function here we have f of x equals 4x over x squared plus 1. Go ahead and take a few seconds and see if you can find the derivative for this particular function. We will be using the quotient rule here just to give you a nudge in the right direction. With a little bit of simplifying, you can see that the derivative here, f prime of x, would be 4 over x squared plus 1, the whole thing, squared. All right, so what do we do here? Well, the first thing we're trying to do is we're trying to make sure, we're trying to find the values where the function is not defined, the derivative is not defined. So that just means, again, we can take the denominator. I've got x squared plus 1 equals 0. I can subtract 1 from both sides, so we'll say f prime of x undefined. I can subtract 1 from both sides. I can take the square root of both sides, x equals plus or minus I. I got some imaginary numbers here. And when you get imaginary numbers, when you're trying to find where f of x is undefined, or f prime of x is undefined even, we don't include those in our answers. So when we say f prime of x is undefined, that's nowhere, which is equivalent to saying f prime of x is continuous. All right, so we don't have any critical values from where the derivative is undefined. Maybe we can find some critical values when the derivative equals 0. So let's check out our derivative here. 4 over x squared plus 1 squared equals 0. So again, I have a fraction. I want to multiply both sides by the denominator and get 4 equals 0. This makes no sense, aka is false. This function has no critical values. There are none here. So again, very quickly, x squared plus 1 squared, x squared plus 1, squared. This canceled here. We're just left with 4 equals 0. Yes, it is entirely possible that a function has no critical values, and this is one of those cases. For the third example, just to bring some trig back into it, here we go. We can take the derivative of this. This is h prime of x equals chain rule here. This would be 2 sine of x, that's the outside function, times the derivative of the inside function. And that's it for the first term. Now the second term here, cosine of x would turn into negative sine of x. So cosine and sine are continuous, so again, we can write here h prime of x is continuous, which means that the derivative has no undefined values. All right. Next, we can set this thing equal to 0. So why don't I do that in blue again? Let's say we have a sine of x, and notice very quickly I can factor out a sine of x. So as long as we can figure out where sine of x equals 0, and we can figure out where 2 cosine x minus 1 equals 0, then we can find our critical values that way. In this, we will just limit it to the first go around on the unit circle, so angles between 0 and 2 pi. So sine of x equals 0 happens when x equals 0 and pi. So here go two critical values. The cosine, 2 cosine x minus 1, if you add 1 and then divide by 2, you'll get cosine of x equals 1/2, right? If you set this equal to 0. And the cosine value equals 1/2 in two different locations on the unit circle. That happens when x equals pi over 3 and when x equals 5 pi over 3. So just within the first go around of the unit circle, we have 4 critical values here. Now you may be wondering, why are critical values so important? So happy you asked. So this may look a lot like the couple slides ago, but with this new information here, we have critical values, and this definition is close to what was on the page a few slides ago. But critical values are important because of the following theorem. We have relative extrema only occur at critical values. So if a function f has a relative minimum or relative maximum at x equals c, then c is a critical value of f. Now, we have some new words here: relative extrema, relative maximum, relative minimum. We also have things called absolute maximum and absolute minimum, and I'm going to go over what those look like in pictures on the next slide. All right, here we have a graph of some function. I'm going to call it f of x. And you might notice that there are some peaks and valleys. And in fact, I'm going to just point those out for you here. There's a peak right here. Oh, there's another peak right here. There's a valley, and there's a valley here. So we have 4 peaks and valleys. Now, peaks are what we're going to call maximum, and valleys are what we're going to call minimum. So here, both of these are what I'm going to call maximum. Maximum. And in fact, the plural, we would say, are maxima. And something very similar for the minimum. So altogether, we can lump maximum values and minimum values into one big group called extrema. So extrema are any maximum or minimum values. So just to get that definition out there. But as you may have guessed, by the title of this slide, we have, what does relative/absolute mean? There's a difference between these maximum values here, this peak and this peak. For this particular function, this here is the highest, the absolute highest point that this graph will ever go. The graph as it continues to the right will not go above this y value. The graph as it continues left will not go above this y value. So that makes this what we say the absolute maximum. That is the exact highest point where it'll go. So absolute max. And similarly, we can call this point down here the absolute min, or the absolute minimum. But you'll notice these two values in the middle here. This is also a maximum, it does top out, and this is also a minimum, it does bottom out. So for those, we call them maximum and minimum, but they're not the maximum of the entire function. They're not the minimum of the entire function. So we just call these relative max and min. So that is the difference between absolute and relative. Now, way over here in this little corner on the bottom right side, absolute max and relative max and min can get kind of weird. So for example, any parabola will have an absolute one or the other, max or min, but it will not have the other. So for example, this particular function, at the vertex here, there's an absolute maximum, but there is no absolute minimum because the function just keeps going down in both directions. Heck, we could even have a function that has no absolute max and no absolute min, being just pick your favorite linear function. It keeps increasing to the right, it keeps decreasing to the left. And so this function has neither a maximum nor a minimum. And if you want to get real wacky, you can have a function called a horizontal line, let's just do this, where every point is a maximum and a minimum. If there's only one y value, every point has the same maximum value and the same minimum value. It gets really weird. That's just more of an FYI. There won't be anything tested on that. Let's move on. Okay, so why know about all of this? Why should you know this? Well, this allows us to easily find max and min values, and we're going to get a little bit into that right this moment, but an applied understanding of why this is important, we will go over in section 3.7, again, in the Larson calculus book. And I think one of the big benefits is that you don't have to make a graph of the function anymore to find the maximum minimum values, or you don't have to remember negative b over 2a to find the x coordinate of the vertex and plug it back in to find the maximum and minimum value of the parabola. It just mathematically simplifies finding maximum and minimum values, which again has real world applications. So how do you do this? On a closed interval, and that's super important. We're talking about if you have a function and you're finding maxes and mins on a closed interval, we have to have square brackets on both sides here. Here are the steps. So here go your 4 steps for finding this out. You have to make sure first and foremost that f, the function, is continuous on that closed interval. You just have to check for holes in the graph or make sure, like a square root function, that we are looking on an appropriate domain or vertical asymptotes. The second thing is you want to find the critical values on the open interval, and I'll have an example of that here coming up in a few minutes. The third thing is you want to plug the critical values and the endpoint values, a and b, the endpoint of our interval, into the original function, because when we are trying to find the max and min of a function, it is of the function, not its derivative. So the only purpose the derivative serves right now is to find critical values. Once you find the critical values, you are done with the derivative. And then from there, once you substitute all these critical values and endpoints into the function, you're just going to get a bunch of y values. The biggest y value, let me write y in there. The biggest y value is the absolute maximum. The smallest y value is the absolute minimum. Now, how do I know that the biggest is the absolute max and the smallest is the absolute min? Well, it's simply because we have what is known as the Extreme Value Theorem. And that says if f is continuous on the closed interval from a to b, then f has both an absolute max and an absolute min. So I just want to give you a few examples of how this works in pictures so you can see what this means. And let me get a few graphs drawn over here. So here are 3 quick examples on how the extreme value theorem works. So this first example, very quickly, we have f of x being this function absolute value of the quantity x minus 3 on this interval from 0 to 5. So in pictures, what this means is that I get to forget about this part of the graph and this part of the graph. And for the extreme value theorem to work, we just have to check, is this graph continuous on this now shortened interval from here to here? And the answer is yes. So we can use the extreme value theorem, and we are guaranteed to find a max and a min, an absolute max and an absolute min. Now the fun part about this is that the absolute maximum or minimum could end up being at an endpoint, or, as we mentioned, at a critical value, because that's where relative maxes and mins happen. So here you can see that we have the endpoints here and here. And the only other thing we would need then is to identify where is the critical value. Are there any critical values? Well, again, critical values are where the derivative is either equal to 0 or undefined. And if a function has a sharp turn in it, that means the derivative is undefined. So we would have a critical value at x equals 3. So here's our critical value. Once you have all the critical values on the open interval, right, we do not include the endpoints as critical values. We can only count critical values between the endpoints. We can then evaluate very quickly f of 0, f of 5, we're always evaluating the endpoints, and the critical value, f of 3. Now just by looking here, I know the y value when x is 0 is 3. I know the y value here when x is 5 is 2. And the y value here when x equals 3 is 0. So we take the endpoints and the critical value and we can figure out what the y values is. Now I just said here, let's look at the graph and figure out what they are. But we can also substitute these numbers into the function, the original function. F of 0, 0 minus 3 is negative 3, absolute value positive 3. F of 5, 5 minus 3 is 2, absolute value of 2 is 2, and so on. From there, we just get to pick the highest and lowest values. So this is the absolute max, and this is the absolute min. And it's that easy. So this next example down here in red, we have a trig function, the beloved trig functions. G of x equals 5 cosine of x. Now, you can already see that we have endpoints of 0 and 4 pi. And that is our interval that I forgot to put here, 0 to 4 pi. Now what we're trying to do is we're trying to find the critical values between those two values, 0 and 4 pi. We cannot use 0 and 4 pi as critical values. So a more step-by-step process would be, how do you find the extreme values? Well, you have to first find the derivative. Well, first let's make sure this is a continuous function. Cosine is a continuous function on any interval that you're given, so check, it's a continuous function. Then, what we have to do to find these extreme values is find all the critical values. So we have to take the derivative, g prime of x equals negative 5 sine of x. We have to set the derivative equal to 0. There we go. We have to solve for x. So we can divide by -5, divide by -5. We still get 0. Sine of x is 0. So at what x values will sine of x be equal to 0? Well, if you remember your unit circle, it could be 0, pi, and 2 pi. And remember, we're trying to find values that are on this interval. Are these the only ones on this interval? No. Let's see. So why don't we keep going? It would be 3 pi, 4 pi. Now if I go over to 5 pi, I'm already outside this interval that we have here. So again, we do not include the endpoints. So these are our critical values right here. And you can see that over here in our function, we have a minimum at pi, a maximum at 2 pi, and a minimum at 3 pi. So that's where all of our critical values are. How does that help us? Well, you can see that if we move across the top here, we have a maximum at 2 pi, and at 0, one of the endpoints, and at 4 pi, the other endpoint. So we have an absolute maximum of 5 at 0, 2 pi, and 4 pi. I want to erase that real quickly and get this a little bit better. Here we go. At x equals 0, 2 pi, and 4 pi. And then we also have minimums here, but I ran out of space, but we could have a minimum of, an absolute minimum of -5 at x equals pi and x equals 3 pi. So the absolute max or the absolute min will be a y value, and the x values are where that maximum or minimum will happen. And I will go through some more detailed examples of this on the next couple slides. This last graph over here is meant to get you to think about where, just by looking at a graph, where are critical values. So it's not only where you have a maximum or a minimum, but it is also where you have a horizontal tangent line. So if we knew the function equation for this h of x here, I would be able to find the derivative, and we would get a critical value at x equals 10 and at x equals 4. So these both would be critical values. And this, of course, is going to be on the interval from 1 to 12. Oops, and it is open on 1 to 12. So here you can see we would have a horizontal tangent line at that point and at this point. And we'll dive into what happens here in the next couple sections, sometime within the next couple sections, where there is a critical value, but it's not a maximum or a minimum. But you'll notice in our definition of the extreme value theorem, if f is continuous on the closed interval, then we can say for sure it has both a maximum and a minimum. But since this is not continuous on the closed interval, it's only continuous on the open interval, we cannot say that it has both. We cannot even say that it'll have one maximum or minimum, one of the either absolute max or absolute minimum. So we can't even say if it has none without actually doing some math or looking at the graph. So this one, of course, has an absolute maximum right here, but there is no absolute minimum. All right, here we have some more space to work with, a few more examples. So the directions are: find the absolute extrema for the following functions on their closed intervals. So this set of directions we will be using into the next slide. So the first thing you want to do is just double check that g of x is continuous, and since the cube root function is continuous and 3x is continuous, when you add or subtract continuous terms together, you get a continuous function. So we'll just say g of x is continuous on the interval -8 to 8. So that being the case, now we can go through and start finding the critical values. So the critical values are where the function is, where the derivative is equal to 0 and where the derivative is undefined. So the derivative by the power rule here is 1 over 3 x to the 2/3 power minus 3. And right away, I can tell that this will be undefined when x equals 0. So we have a critical value over here. It would be x equals 0. And if you set the derivative equal to 0, I'm going to multiply everything by 3x to the 2/3 power, so I can get rid of the fraction. So I will have 1 minus 9x to the 2/3 power equals 0. So if I solve for this, I'll have negative 9x to the 2/3 power equals -1, divide by -9, that's x to the 2/3 power equals 1 over 9, and I can raise this to the reciprocal power to get x equals 1 over 9 to the 3/2 power. Now bringing back what it means to have a 3/2 power, the 2 means we will, or the denominator means we will take the root of what's in here and then we will raise it to the numerator power. So if I take the square root of 1 over 9, I'll get 1/3. And if I cube the fraction 1/3, I will get 1 over 27. So the other critical value here is 1 over 27. Now, how do we find the absolute max and absolute min? Well, we take our critical values and our endpoints, a and b, and we substitute them into the original function, right? The derivative here is only useful for when you're finding critical values. So we found our critical values. I'm done with this. No more derivative. Now we have to go back to the original function and we can find these. So here we are using the original function to find the maximum and minimum value of the original function. So with that, we will substitute -8 into this function. And when you take the cube root of a negative number, you're allowed to do that. It just ends up being negative. So the cube root of -8 is -2. Negative 3 times -8 is 24, so that's 24, and a -2 would be a positive 22. And we can do something very similar for 8. We can substitute in 8 and get -22. We can substitute in 0 and get 0. We can substitute in 1 over 27 and get 2/9. So how that works very quickly, 1 over 27, the cube root of that, we could take the cube root of 1 and get 1, and the cube root of 27 and get 3. So the cube root of 1 over 27 is 1/3, minus 3 times 1 over 27. Well, you can multiply the 3 times the 1 and get 3. 3 over 27 is 1/9. So 1/3 minus 1/9 is 2/9. So then we just have to pick the biggest and smallest value. That being here, this would be our absolute max and our absolute min. It just happens to be that they are at the endpoints. Cool. We still have to check the critical values. So don't start getting lazy and only checking the endpoint. We have to do a derivative. We are in a chapter using derivatives. It makes sense to find a derivative. Then we have to find out where the derivative is undefined and where the derivative equals 0. We will test the endpoints and the critical values and pick a max and min from there. Let's look at a couple more examples. So here we have the same directions, and the first thing you always want to look for is the function continuous on its interval? Well, it seems as though with this particular function here, h of x cannot equal -3. If you set this equal to 0, you can see that x cannot be equal to -3. But that being said, -3 is not on this interval. We can say, or it's not in this interval. So yeah, we are guaranteed to have an absolute max and an absolute min. So let's go through this process to figure out how we can find it. So first thing we need to do is make sure we state it just it might be pretty obvious, but make the time to write out the statement very quickly. The function is continuous on this interval. The next thing we need to do is find the derivative, and I'm just going to let you pause the video and try it, and I'm just going to put the derivative up here without any work. So here's the derivative for h of x, as you can see. There we go. Now, one thing that I have not yet had the chance to explain is that when a function has a discontinuity, right here it was discontinuous at x equals -3. If we try to put -3 in here, we get an undefined value. There's a vertical asymptote there. There's a lot of different ways to say that. Well, if you find the derivative of a function that has a discontinuity, the derivative will also have that same discontinuity, and you can see it right here. This derivative is undefined at x equals -3. So that automatically, even without finding the derivative, this tells us where there will be a critical value down here. So I'm going to write it. There is a critical value at x equals -3, and in fact that is the only critical value that we have here. If you set the derivative equal to 0, you would multiply the equation by x plus 3 squared, and you would just get 3 equals 0, thereby not giving us any other critical value, similar to a previous example you saw in this video. So from there, we have this one critical value. Guess what? It's not in the interval still. So this is still not in our interval. So the only way, or the only values we have that we can find for a max and a min here are our endpoints. So we are always going to have our endpoints, but we may or may not have a critical value that is usable. So with this, we can just find h of -1 and get -1/2, because I'm putting these back into the original function. Remember, the derivative here is only good to be finding critical values. We've done that already. Now we're back up here working with the original function. So from there, we can find h of 6, which would be a positive 2/3 if you just substitute 6 in up here. And finally, we can just say the absolute minimum is -1/2, and the absolute maximum is 2/3 for this particular function on this interval. So lastly here, for this type of example, we have f of p. And yes, we are going to break this down into a piecewise function because that is what absolute values tell you to do. So I've got p plus 4, and I have a negative p plus 4. This is if p is greater than or equal to -4, and this is if p is less than -4. So absolute value functions, to answer our question, is this function continuous? Yes, absolute value functions are continuous. Fine. So we have this particular absolute value function. How did I get this value over here? Well, I just take the inside of the absolute value, set it equal to 0, solve for p. That's where this value comes from. This is where the sharp turn is. All right, so now that we know that, we can, like I've been trying to do here, state that f of p is continuous on -7 to 1. Now that we have broken it down into a function that makes more sense to take a derivative of, at least, we can take the derivative of this. We can find f prime of p equals 1 and -1. Again, this is for if p is greater than or equal to -4 and if p is less than -4. So we don't have to worry about taking the derivative of this side of things. This is just telling us where the derivatives will exist, just like where these functions exist. So right now then, we can look at each individual piece to see if there are any discontinuities within there. So the derivative for when p is greater than or equal to -4 is 1. Well, that's not, there are no critical values for this function. When it is less than -4, we have -1. There are no critical values for that function. But when you look here, there is a critical value because the derivative has a discontinuity between, or at p equal to -4. So just really quickly looking at a graph of this, this would look something like this. Here's p, here's f of p, aka y, and at -4, we have a graph that looks something like this. That's -1, this is +1. And since we have this discontinuity, aka the function is not differentiable at -4, aka there's a sharp turn at -4, the derivative does not exist there, which means we have a critical value at p equal to -4. And this is our only critical value. So we can find f of -7, we can find f of 1 because you're always going to have your endpoints, and then we can find f of -4. And when we put all of these into our function, -7 in here, -7 and 4 is -3, absolute value of -3 is +3, whoops. If you put 1 in there, you'll get 5, and if you put -4 into the original function, you'll get 0. So here's your absolute max, and here is your absolute, absolute min. All right, one more example. I know you guys are gonna love it. Here we go. Last example. There's a lot going on with this because I'm sure a lot of students out there have forgotten what this graph represents. So we're trying to find an absolute extrema on the interval. Is this a continuous graph on -2 to 2? Well, yeah, it sure is. If you wanted to know what this looks like as a graph, this is a semicircle. In fact, it's the top half of a semicircle because it's positive, from -2 to 2. So yeah, it is absolutely continuous. How did I know it was the radius was gonna be 2? Well, I can just look at the square root of this number right here. The square root of 4 is 2, so I know the radius was going to be 2. All right, so here we go. We are asked to find the absolute extrema for each of these intervals. There are 3 intervals over here we're going to check out. All right, so let's find the derivative of f of x. Go ahead, pause the video, try it. It's going to involve a chain rule. Please tell me you saw it was going to involve a chain rule. Find that derivative, and I'll put it up here in just a few seconds. All right, here's a derivative. The power, or I guess you could say the chain rule, the generalized power rule was used here because this is equal to 4 minus x squared to the 1/2 power. If you subtract 1 from this exponent, right, move it to the front, that's where the 1/2 is. Subtract 1, it becomes negative 1/2. This whole expression moves down to the bottom with a 1/2 power. For whatever reason, I changed it back into a square root. Sorry, not sorry. Then you have to take the derivative of the inside function, which I just realized should be a negative 2x. All right, so then if you want to do a very quick little simplification, you can in fact cancel this 2 with this 2 and get a final derivative of this. And yeah, I'm really going to mess with you guys out there. The square root is the same thing as the 1/2. I don't know why I changed it to a square root here, so I fixed it here. Now, we have to find what the critical values of this function are. And we're only interested, again, finding critical values that are not the endpoints. So we're just trying to find critical values between the endpoints, aka on the open interval. So if we do that, first thing I notice is that there's a denominator here, so I've got to set that denominator equal to 0 and solve for x. So I've got 4 minus x squared to the 1/2 equals 0. So this is where the derivative is undefined, aka where the original function is not differentiable. So you can square both sides, you'll get 4 minus x squared equals 0. You can add x squared to both sides. You can take the square root of both sides, plus or minus 2. X equals plus or minus 2. Well, that stinks because our interval goes from negative 2 to 2. We are looking for critical values that are not the endpoint values, so neither of these help. So, all right, so those don't help us. Those are already the endpoints. So the other thing we can do is find out where the derivative equals 0. So if I multiply both sides by the denominator, we're just going to end up with negative x equals 0, which tells us x equals 0. And that's the only critical value that we will have that is between our endpoints. All right, so with this particular critical value, x equals 0, that is right here on the graph. That means there's a maximum or a minimum there. So let's go through and just figure out what's going on here. If I have f of 2, and again, I'm done with the derivative. We are no longer using the derivative. It has served its purpose in giving us critical values. All right. So if we're just trying to find absolute extrema, we can substitute now the endpoints into the original function and the critical values into the original function. So here we are, we have 2 absolute minimum and 1 absolute maximum. So again, we can have a minimum that happens in more than one place, that's fine. And we have a maximum here, guess what? It's 2. I don't think that's going to be too surprising if you understand / remember how a circle works. Okay, so this is our answer for the closed interval -2 to 2. Say, for example, we talk about this particular interval. Let's give it a different color. -2 to 0, but we leave 0 open. We leave that side open. So as far as the graph is concerned, we're looking at something like this now. There we go. Since the highest point on this graph here is no longer included, we no longer have an absolute maximum. We have an absolute minimum for sure, but we do not have an absolute maximum anymore. So for the interval -2 to 0, we only have an absolute minimum, and that will be at -2, 0. Now I want you guys to understand that there is a difference here. This is an interval. This is a location. It would look something like this. In fact, it would look exactly like this one here. F of -2 equals 0. All right, lastly, give this last interval a shot. See if you can find an absolute minimum or an absolute maximum or both or none. And I'll be back in a few seconds with the answer. So for this last one on the open interval, it would look something like this. We would have 2 open dots, one on each end, leaving us with only a maximum. So on the interval -2 to 2, we only have an absolute maximum. And that would be at f of 0 equals 2, or the point ordered pair 0, 2. Now one last challenge exercise. Can you find an interval on this particular graph with this particular function? Can you find an interval that will not have either an absolute maximum nor an absolute minimum? Take a few seconds, think about it, and I'll be back with some possible answers. So for that last question, yes, there are tons of intervals that work. Like infinite number of intervals that you could come up with out there. One interval could be 0 to 2. Another interval could be, 1 to 1.5. And there are lots of intervals that would work as long as you do not include the 0 point. Because if you go from -1 to 1 and you put open intervals on both sides, it's fine, there won't be a minimum. Or heck, even from -2 to 1, there won't be a minimum if you leave both sides of the interval open. But if you include this point, there will always be a maximum. So as long as you're picking 2 numbers between -2 and 0, or 2 numbers between 0 and 2, you will never have a maximum or a minimum. Which is why it is super important to understand and recognize that the interval you have, if you want to be guaranteed a maximum in, you have to have a closed interval. Good luck, everybody.